Welcome back. So we have completed this Turing enumerable procedure. Okay. Now we'll go for membership algorithm, then lexicographic order, closure properties, L and L bar theorem. So after that we will go to Chomsky hierarchy. Once I complete the Chomsky hierarchy, we will see all the properties. Okay. With that, this topic will be completed. Only one topic will be left, that is undecidability. Okay. This is after this membership algorithm. Membership algorithm. It is used to list all the members as well as non-members Okay. It is used to list all the members as well as non-members. Okay. So actually undecidable languages, they don't have membership algorithm. Undecidable language means what? REL. REL don't have membership algorithm. Only REC. REC will have membership algorithm. What is membership algorithm? A given string, already we have discussed, a given string W and a language L. Okay. So it is the process of checking if a given string is given and a language L is given, okay, then it is the process of checking whether W belongs to L or not. So here that is REL, recursively enumerable languages, they don't have membership algorithm. Undecidable languages don't have membership algorithm. So if a language L has membership algorithm, then it is said to be REC, because decidable languages only will have membership algorithm. I repeat, okay, here a language L is said to be REC, recursive. Okay, if it has membership algorithm. So definitely if a language L is having membership algorithm, implies its complement is also will have, okay, implies L bar is also have L bar also will have membership algorithm. So decidable languages only will have membership algorithm. Okay, undecidable languages. So you can say therefore a language, So based on this, you can write like this also. A language L is said to be REC, okay, if and only if both L and L bar, L and L bar has membership algorithm. Okay, na? See guys, a language, any language, if it has membership algorithm, it is said to be REC. If a language has membership algorithm, its complement also definitely will have membership algorithm. Okay, so you can say like this or say simply like this. A language is said to be recursive if it has membership algorithm. Whenever membership algorithm for there exists for L, its complement also will have. Okay, na? So undecidable languages, undecidable languages, that is REL, won't have membership algorithm. Okay, next, copy this. If anybody has any doubts in this, you can watch the recorded video. Okay, that part. Copy this. Okay. Hello. Neither L nor L bar means L is not having RE. If L bar is also not having RE, L is not having TEP. L is not having TEP means, okay, L is not having TEP means neither means nor means they don't have TEP. If suppose here what did I say? L has no TEP. L has no TEP means L is not RE. Okay. L bar is also not having TEP. This L bar is not RE. If both L and L bar is not RE, then L is said to be non-RE. Okay. So we will discuss again. See in this. Okay, we do one thing. We will discuss in this complement of this this part. Where is that? In this you will understand L and L bar theorem. Okay, na? So generally, if L is not having TEP, then it is said to be not RE. Okay. If L bar is also not TEP, then definitely L is non-RE. So copy this one. Okay. Now, a language, this is, okay, undecidable languages, REL, won't have membership algorithm. Only recursive language will have membership algorithm. Next, lexicographic ordering. Lexicographic order. If I keep on seeing every message, it will take so much of time. So these kind of simple doubts, you can watch the recorded video. Okay, I cannot repeat same again and again. Take lexicographic order. So REL don't have any lexicographic order. L is said to be recursive if and only if L can be enumerated in some lexicographic order or alphabetic order. Alphabetic order or dictionary order. Okay, now, okay, L is said to be recursive if and only if L can be enumerated in some lexicographic ordering or alphabetic ordering or dictionary ordering. Okay, now, so example, you see sigma equal to A comma B. So what is sigma star? Sigma star is all combinations of A and B. So we can write in all combinations of sigma star in lexicographic order, that is epsilon, the smallest string, then A, then B, then CAA, AB, then BA, BB, so then again triple A. So you don't think that, sir, in dictionary order A comes, after double A comes, double A after the triple A comes, triple A after 4A comes. Of course, it is dictionary order. Okay, but here in that case, if you go for in dictionary, the words are finite, but here these are infinite, na? So how can I write infinite? So that is the reason I am going for length increasing order in dictionary order. Okay, na? So length, so first length 0, epsilon, then length 1 A, B, length 2 AA, AB, BA, BB, then triple A, then double A, B. Okay, like this. Okay, so here if a language is said to be recursive if you can, okay, if it is enumerated in some lexicographic order, some enumeration procedure. Okay, copy. So here sigma star is regular, but if a language is in lexicographic order, it need not be regular. It can be recursive. Are you following? It doesn't mean that, sir, this is regular, so every recursive is regular. No. It is if a language is in lexicographic order, so can we say regular? No. So a language lexicographic order, it doesn't mean that it is a regular. It is recursive. Okay. Yeah. This is BB. Next. So we have done. Now we'll go for closure properties. Closure properties. Closure properties of REC and REL. Now take recursive languages. Recursive languages are closed under union intersection concatenation cleans closure positive closure union intersection concatenation cleans closure positive closure set difference okay. Union intersection concatenation cleans closure positive closure set difference quotient and complement. Next. Union recursively enumerable languages are closed under union intersection concatenation cleans closure okay. Now here main important is this one. Here recursively enumerable languages are not closed under not closed under complement and set difference. Remember, whenever any language, if it is not closed under complement, automatically not closed under set difference also. Why? Because what is L1 minus L2? L1 minus L2 is L1 intersection L2 bar. When it is not closed complement, then how can we say that L1 intersection L2 bar is closed? So that is the reason, because here see, now complement is not closed, then intersection is also not closed. Means this total, don't say intersection is closed, but because of this complement is not closed, this total may not be REL. Okay na? So that is the reason. Whenever a language is not closed under complement, go for set difference also. Not closed under complement and set difference. Okay guys? Now these are about the closure properties. Copy. Now we'll go for L and L bar theorem. Okay, next, copied. Guys, look at this. L and L bar theorem. See, guys, every recursive language is also RE. Okay, every recursive language also RE, but every RE language, recursive language, may not be REC. Okay, now you know this one. Every REC is also, example, I have given this now. Here, this REC, every REC is also RE, but every RE may not be REC. Every REC is also RE, but every RE, suppose a language is here, it is not in this small circle, it is in second circle. So it is RE, it is RE, but not REC. Whereas if a language is here, it is REC and also RE. So every REC is also RE, but every RE may not be REC. Okay. Now, every recursive language also RE, recursive enable, but every recursive enable may not be REC. Okay, na? Next point. If L is recursive, implies L bar is also recursive, because the recursive languages are closed under complement. Recursive languages are closed under. Okay, recursive languages are closed under. Okay, union, intersection, concatenation, clean closure, positive closure, set difference, and also complement. Okay, na? So I repeat guys, recursive languages are closed under complement. Okay, whereas recursively enumerable languages are not closed under complement and set difference. Okay, na? I repeat, if a language L is recursive, its complement is also recursive. Okay, whereas if a language is REL, its complement may be, may not be. So never say that it is never, means not closed. Suppose regular languages are not closed under subset. Actually, no language is closed. No language means regular, DCFL, CFL, CSL, REC, REL. No languages are closed under subset, superset, infinite union, infinite intersection, infinite set difference. But it is not every time. Example, A power n, B power, A power m, A power m, B power n, A power m, B power n. It is not. It is regular. Okay, but it's subset. It's subset. I am taking a subset. A power m, B power 2n. It is also subset, na? So this is regular only. This is regular. L dash is subset to L. But whereas L double dash, A power n, B power n, this is not regular. So a subset not closed means what? Always not true. Okay. So REL or not closed under complement means if L is RE, it implies L bar, no guarantee that it is also RE. It may be RE, may not be RE, may or may not be RE. At the same time, if L is REC, then 100% L bar is also REC. Do you understand? So if a language is REL, its complement may be, may not be. If a language is REC, its complement is also REC. Okay, now we'll go back. So here, every recursive language is also RE, but every REL may be RE, may or may not be REC. Now, if L is recursive, L bar is also 100% recursive. Next, if L is RE, then its complement L bar may or may not be RE. So don't say that if L is RE, its complement never be RE. No. Okay, na? If a language is RE, its complement may or may not be RE. Whereas L is recursive, L bar is also recursive. Now, if L is recursive, it is 100% RE, also RE. If a language is RE, it may or may not be REC. Are you clear? I repeat, a language L is recursive, 100% its complement is also recursive. Now, if a language is REL, its complement may or may not be REL. Okay. If a language is REC, 100% is also RE. If a language is RE, it may or may not be REC. Now, this is main point. If a language L and its complement L bar. Are you following? If a language L and its complement L bar both are REL means actually guys, if language RE, L bar may be or may not be RE. Okay na? Okay, sometimes it may be, sometimes may not be. Suppose if a language L and its complement L bar both are RE, and now guys again, if a language REC 100% L is also RE. If a language RE, it may or may not be REC. But every RE may not be REC. Okay na? Now come to this one. If a language RE, its complement may or may not be RE. Suppose a language L and its complement both are RE, then L is 100% REC. Are you following? If a language is RE, it may not be REC. If a language RE, its complement may not be RE. Suppose a language L, its complement L bar, both are, its complement L bar, a language L, its complement L bar, both are RE, then L is REC. And if a language REC, its complement is also, L bar is also REC. This is L and L bar theorem, okay? Okay guys, copy this. Okay, copied. Next. Now, I'll give you one question. If two languages if a language L and its complement L bar, one second, if L bar, okay, if a language L and its complement L bar are given, then which are the following cases can be true? Which of the following cases can be true? Option A, both L and L bar are REC. Both L and L bar are non-RE. C, one of the one of among L and L bar, one of them is RE, but not REC. One of them is RE but not REC, and the other language is non-RE. Okay, then D. Both of them are RE. Both of them are RE, but not REC. Both of them are RE, but not REC. E. One of them is RE and also REC, but the other one is not REC. Let me check the options. Both L and R are REC. Okay. Take these options. Copy. Yes, guys, already I told you TOC, theory of computation. Once you understand, it is very easy. But again and again you have to, even though you understand now, there is a lot of chances to forget this one. Okay, na? You have to revise, that's it. Okay, guys, listen. If a language, see this is REC, this is RE, this is non-RE. Okay, now if a language is, if L is, if L is REC, if L is REC, implies L bar is also REC, because the here I told you L is REC implies L bar is also REC. Yes, both languages can be REC. It is true. It is true. Are you following? If a language is recursive, its complement is also recursive. Okay. Now, because recursive languages are closed under complement. Okay. Both L and L bar are non-RE. Suppose a language is here. Its complement may be here, okay na? So need not be, if L is RE, if L is non-RE, if L is non-RE, implies its complement need not be a non-RE. It can be RE, it can be non-RE also. L bar can be, or L bar may be non-RE. Yes, chances is there. May be non-RE. Okay na? If a language is here, its complement also may be here. Okay na? So if L is non-RE, its complement is also non-RE. Yes, it is true. It is true. Okay na? Now, among L and L bar, one of them is RE but not REC means, okay. So here in the C option, among L and L bar, okay, L and L bar, one of them is RE but not REC. The other language is not RE. Okay, guys, listen. What is this here? Here it is given that L is RE but not REC. But not REC means L is here. Okay na? One of them among L and L bar, one of them is RE. So suppose L is RE but not REC. The other language is not RE. Okay. So what he is saying that L is RE. Are you following? L is RE means here but not REC. And he is saying that if L is here and L bar is also L bar will be non-RE. The other language non-RE. So we do one thing. And here let us take L is here and L bar is also here. Are you following? Suppose is saying that L is RE but not REC. Okay, so here I have to take, okay, and the other language is not RE. Okay, I will say, so suppose he is saying that it is not RE. I say that it is also RE. Okay, I will take L bar is also here. Now I have told you, if L and L bar both are RE, L and L bar both are RE. Okay, now if L and L bar both are RE, then what is L? L is REC. L bar is also REC. But it is given that L is RE but not REC na. So are you following, guys? If L and L bar both are RE, yes, I have taken here, then L must be REC and L bar is also REC. But what is the given? L is not REC. Then if L is not REC, L is RE, then L bar cannot be here. L bar only, it must be here. Only. Yes, among L and L bar, if one is RE and not REC, suppose L is RE but not REC, then L bar cannot be in RE. So L bar is not RE. Yes, this is also true. Now both of them are RE but not REC. both of them means okay, same here, both of them here, but not REC. Already I told you, if a language L and its complement L bar both are RE, then both of them must be REC. But it is given that, but not REC. False. Okay, one of them RE and also REC, but the other one is not REC. Okay na? So one of them is RE and also REC means I will take this one. So means he is saying that L is here. See, one of them is RE and also REC here. But the other one is not REC. Means what? L is REC and L bar is saying that not REC. Can means L bar here or here. Okay. So how it is possible? If a language is REC, its complement is also, if a language is REC, its complement is also REC. Therefore, it is also false. So answers are A, B, C are the right answers. Okay. Good. Very good. How to memorize today's theory part of TOC? So एक बार एक काम करो, कल आपको ये रिकॉर्डेड वीडियो मिलेगा ना, बार बार देखिए, आपको याद रखेगा. अदरवाइज नोट्स अब जो लेकर ना वो पढ़िए. हाउ कैन आई से? सो दीज आर द फर्स्ट टाइम यू आर लिसनिंग ना, यू हैव टू गो फॉर रिविजन मैम, रिवाइज करो. ओके. See, I am not the God. I have not invented the TOC. Somebody great person has invented, and they have written that this much, and that in that I am giving you this much. In this you are receiving in this much. So how I remembered? Even I have done this a lot of hard work. So if you also do hard work, you will become more stronger than me. Okay. Revision is required, ma'am, for this. Okay. Subi, you understand? Here both L and L bar are non-RE. Means guys, one is done. First one is done. Okay, L is here and L bar is also here. Suppose L is here. Its complement is also suppose here. It is not possible. It either the complement is also, if L and L bar RE, then only the case is they must be in this region or they must be in this region. But L and L bar both are in this region, never possible. A language L is RE but not REC, and L bar is also RE but not REC, never possible. If a language L and its complement both are RE, means both are REC. That's it. There is no other option. If a language L and L bar both are RE, means L is REC. Otherwise, they can be outside of RE. They can be outside of RE or inside of REC, but not here. Okay. Chalo, we'll go to next one. That's all. Recursive and recursive language completed. We'll go to next, Chomsky hierarchy. Say Guys, listen. Every regular is also DCFL, but every DCFL is not regular. Are you following this, guys? Here, this is regular. Every regular, every regular, every regular is also DCFL, but every DCFL may not be regular. And every regular DCFL also CFL. But if a language CFL, it may or may not be DCFL and regular. And every regular DCFL, CFL also CSL. Every CSL may not be CFL. Okay. Every CSL also REC, but an REC may not be this. And all these languages also RE, but every RE may not be REC, may not be CSL, may not be CFL, may not be CFL. You can understand because you know what is what. Regular language accepted by what? Regular language accepted by what? Accepted by what? Accepted by finite automata. And DCFL by DPDA. Okay. And CFL by PDA and CSL by linear bounded automata. This is by halting Turing machine and this is by Turing machine. Okay, na? This is Chomsky hierarchy. Okay, Chomsky hierarchy. Cover this. चले copied. Okay. Now, guys, the union of regular with DCFL, regular union DCFL gives you DCFL. I told you the every language is closed under union with regular, union intersection with regular, set difference with regular means regular union DCFL or regular means intersection DCFL gives you DCFL, gives you DCFL means regular intersection DCFL or regular union DCFL, or regular minus DCFL, or DCFL minus regular, always DCFL. Similarly, regular operation with CFL will give you CFL. But there is, I told you one problem. Regular L1 and CFL L2. L1 minus L2 is not a CFL. I have explained this clearly. You can go because regular minus CFL. Okay, this is what regular intersection CFL. CFL complement is not CFL, then we will go for CSL. So the next level, this the superset of CFL. Okay, if any language is not closed under any property, then go for the superset. CFL next superset is CSL. So CSL complement is CSL. So regular intersection CSL will be CSL. This part I have told you. Okay, now guys, I have explained this. You can go to this. That where properties of CFL I told you. Now listen guys. Generally union of regular with CFL is CFL na? Just now I told you. Okay, example, let L1 equal to a power n b power n greater than 0. Okay, what is this guys? Hello, it is CFL na? CFL. Okay, now what is this a plus b whole star? A plus b whole star. What is this a plus b whole star? Is regular. A plus b whole star is regular. So one is CFL, the other one is regular. CFL union regular means what did I say here? Here I told you regular union CFL is CFL. This is fixed, no doubt in this. So in general, whenever a statement is given, the union of a CFL with regular is CFL. I repeat, the union of a regular with CFL is CFL, no doubt. Okay. Suppose given L1 is CFL, no doubt. L2 is regular, no doubt, because it is finite or we can accept it is PDA. Now what is L1 union L2? CFL union regular is CFL. So L1 union is L2 is CFL. So it is not a proper answer. It is not a perfect answer. Of course, it is an answer, but not perfect. So in the options, if it is there, what L1 union L2 is, if they ask you like this, A CFL, B regular, okay, and C may be regular, okay, and D may be CFL. If options are given like this, okay, then listen guys, whenever languages are given, go for actual operation. Remember this point. Go for actual operation. Okay, na? So languages are given. L1 is given. L2 is given. So what is L1 union L2? What is L1 union L2? CFL union regular is CFL. If you go for this, it is a wrong answer. It is a wrong answer. Are you following? Now guys, here, what is L1? What is L1? A power n, B power n. What is L2? A plus B whole star. So L1, A power n, B power n, union A plus B whole star. What is the A power n, B power n, union A plus B whole star? What is A plus B whole star? A plus B whole star is everything, na? Everything. So whatever you you add this to this one, you will get A plus B whole star only. Nothing else you will get. So which is regular. Okay, na? So guys, whenever languages are given, go for the actual operation. Okay, na? Go for the actual operation. So answer is what here? It is regular. Sir, but according to this, it must be CFL, na? Of course, Regular is also CFL, na? Regular also CFL. If it is MSQ, you go for both. If it is MCQ, the best one answer is, example, if anybody asks, I am in Delhi. If I say I am in India, India is also correct. I am in Delhi, Delhi is also correct. So more accurate, I am in Delhi. Are you following? So it is regular and also CFL. But if I say I am in Delhi, I am in India, I may be in Delhi, I may be in my hometown Visakhapatnam or anywhere. Are you following? So accurate that this year, if L1 and L2 is CFL, of course CFL, but it's not a proper answer. The proper answer is regular. And if it is MSQ, then go for both. If it is MCQ, go for only regular. Okay, na? So whenever two languages are given, in general, L1 is regular, L2 is CFL. Then what is L1 minus L2? Again, there is a problem. In general, in here, three types of questions I can give you. Same question, three ways. The subtraction, the set difference of a CFL with regular. The set difference of a CFL with regular is CFL. But if they ask you like this, L1 is regular and L2 is CFL, then what is L1 minus L2? Oh, so set difference of a CFL with regular is CFL. Wrong answer. Whenever they ask you like this, L1 minus L2 is L1 intersection L2 bar. So regular intersection CFL complement. CFL complement is not a CFL. Then we will go for upgradation CSL. So answer will be CSL. Instead of giving like this, if they ask, if they don't give you, what is the set difference of a CFL with regular? Then you can go for. Otherwise, at the same time, if L1 equal to something, L2 equal to something is given, whenever the two languages are given properly, you go for the actual operation. Find the actual operation, either union or intersection or subtraction, whatever. Okay, na? So that's all, guys. We'll go for next concept. So I think you have copied, na? All these. Sir, you are in Saket is also correct. So Rasik Mishra, you are from Delhi or what? Now, properties of languages. Properties of all languages, okay? Take this. Example, I'll give you one more. Whenever two languages are given, let L1 is RE, and L2 is REC, then L1 minus L2, then L1 minus L2 is, okay. If the question is like this, what is L1 minus L2? L1 minus L2 is L1 intersection L2 bar. What is L1? RE intersection L2. What is L2? Okay, REC complement. REC recursive languages are closed under complement. So REC complement is also REC. You are taking intersection of two different languages. Are you following? L1 is RE, L2 is REC. What is L1 minus L2? L1 minus L2 is L1 intersection L2 bar. What is L1? RE. What is L2? REC. REC complement is also what? REC. So RE intersection REC. Okay. So here whenever two different languages are given, whenever two different languages you are getting any operation, if you are doing any operation between two different languages, so RE and REC. So go for this. Which one is the superset? RE. Every REC is also RE. When you are doing operation between two different sets, then go for the upgradation. So shall I go for RE to REC or REC to RE? So REC, every REC is also RE. So I will go for the upgradation. RE. So RE is already RE. REC, I'll go for upgradation. REC, every REC also RE. RE and RE. The RE languages are closed under intersection. RE languages are closed under intersection. Only they are not closed under complement. Why it is? Oh. Shit. Yeah, here, see, RE languages are not closed under complement and set difference. They are closed under intersection. Okay, na? They are closed under intersection. Now come to this one. Here, what did I give? So here, L1 minus L2. Okay. So what is L1? RE and L2 REC. Complement is REC. REC complement is also REC. But you are doing the operation between two different languages. Then go for the upgradation of REC. REC is RE and RE intersection RE is RE. Okay. You understand? Okay. You can take this question also. Okay. Now I will go to next. So properties of all languages. Look at this. This is union, intersection, concatenation, cleans closure, positive closure, complement, set difference, reversal, homomorphism, inverse homomorphism, subset, superset, infinite union, infinite intersection, and infinite set difference. Okay, na? So guys, you do you want me to more? Okay. So take this structure, guys. Copy this. Regular, DCFL, CFL, CSL, REC, REL. You know this order. Okay. Regular, DCFL, CFL, CSL, REC, REL. So order, you need not to maintain any order. Just you can write any order. So union, intersection, dot, that is concatenation. This is cleans closure, positive closure, complement, set difference, reversal, homomorphism, inverse homomorphism, subset, superset, infinite union, infinite intersection, infinite set difference. Okay, na? Saurya Bhatnagar, how can you say that? See, every REC, see, how can you take RE is superset of REC? superset of RE. Don't go for Venn diagram. Suppose in college days, I mean in school level, this is A, this is B, A intersection B is B only, 100% perfect. But here, if this is CFL, and this is regular, then CFL intersection regular is CFL only. It is not regular. It is not regular. Sometimes maybe, but not regular. Okay, na? Now listen. When it is given that this is RE, this is REC, this is two different languages. So this superset is this one. Then you have to go for upgrade. When I go for upgrade, this also RE intersection. Why? Because this year, what is the question? RE intersection REC. Here, this language may not be REC, na? Every RE may not be REC, but every REC is also RE. So that is the reason we go for upgradation. RE intersection RE is RE. So don't go for Venn diagram. Okay, if you are thinking in Venn diagram way, that is not correct. Okay, next. Copied? Now guys, listen. Yeah, right, Subi. Now, regular languages are closed under every operation. Regular languages are closed under every operation except this subset, superset, infinite union, infinite intersection, infinite subtraction. Okay, no language is closed under subset, superset, infinite union, infinite intersection, infinite subtraction. So I can mark this as not closed in all these languages, because no language is closed under subset, superset, infinite union, infinite subtraction. No language is closed. Okay, na? Next. So have you copied this one? Next, DCFL. DCFL are closed under only two operations. DCFL closed under what? Where? Complement and inverse homomorphism. DCFLs are closed under complement. This is DCFL. Complement. Closed under complement and inverse homomorphism. Here. Are you following? DCFLs are closed under complement and inverse homomorphism, whereas that is not closed under in other cases. So union not closed, intersection not closed, concatenation is not closed, cleans clause not closed, positive not closed, set difference not closed, reverse is not closed, and homomorphism also not closed. Only closed under two operations. That is here. Okay, so DCFL are closed under only complement and inverse homomorphism, whereas CFL, where CFL not closed, CFLs are not closed under intersection and complement, and also set difference. Okay, and CFLs are closed under union, concatenation, cleans closure, positive closure, then reversal, homomorphism, inverse homomorphism, but they are not closed under intersection and complement and set difference. You can copy this. Okay, guys. Copied. Next, see here, no language is closed under subset, superset, infinite union, infinite section, infinite set difference. No language closed. Even regular also not closed. Okay. Now go for next one. CSL. CSLR. See, actually there is now till now reversal and homomorphism, inverse homomorphism. Some places they will give as closed, but here there is not clear now. Till now it is not clear, so it is still doubts. So that is the reason I am giving this as no information. Here CSL, REC, context sensitive REC, REL, and under operation under reversal, homomorphism, inverse homomorphism, these I am giving as no information. No information. Okay, no information. Next, CSL, are closed under all operations, closed here. It is closed, it is also closed. So closed only, we don't, it is not closed under these subset, superset and all these, and also no information about homomorphism, inverse homomorphism, reversal. And recursive is also closed under all, and REL not closed under complement and set difference. Already we have discussed. So complement and set difference not closed, because if L is RE, its complement may not be RE. When its complement is not RE, automatically set difference also not closed. Okay. Then whereas closed under union, intersection, concatenation, cleans closure, positive closure. Okay. So copy this, guys. Not REC means it is RE or non-RE. Intersection RE, how can be REC? Soumya Bhatnakar. How it is possible? Not REC, intersection RE. You are saying about level. Above level, how can be it is? RE and not REC. Not REC means what? It can be RE or non-RE. So RE intersection non-RE, it will be non-RE. Simple. Any operation between two different languages, go for the above superset language. Okay, na? This is about properties of all languages, guys. Okay. Next, we have done. So almost, so not almost completely. We have done this part. So not complete, not left anything. If you have any doubts, you can ask me. So in Turing machine, we have done the design part, then variations of Turing machine, types of Turing machine, halting Turing machine. Okay. Next. Okay, sorry. So what I'm saying, design of Turing machine, then variation of Turing machine, halting Turing machine, then linear bounded automata, non-deterministic Turing machine, then Church's Turing thesis, then universal Turing machine, then REC and RE, and what is REC, what is RE, and their properties. Okay, that is Turing enumerator procedure, lexicographic order, membership algorithm, closure properties, L and L-bar theorem, all we have done. Chomsky hierarchy we have done. Then all the properties. Okay, then we'll go for next new topic, that is undecidability. Okay, undecidability. Undecidability. Guys, it is also simple. It is important topic. Decidability. Decidability. Okay. A problem is said to be decidable if there exists an algorithm to solve that problem. A problem is said to be decidable if there exists an algorithm to solve that problem. Or you can say a problem, you can give like this, or a problem is said to be decidable if there exists a STM, halting Turing machine, to solve that problem. Okay, to solve that problem, you can say like a problem is said to be decidable if there exists an algorithm to solve that problem, or an STM to solve that problem. You can say anyway. Okay, now undecidability. A problem is said to be undecidable if there exists a procedure procedure to solve that problem. To solve that problem. Okay? To solve that problem. If algorithm is there, algorithm means what? Always stops, always halts. So then the problem is said to be decidable. If procedure is there, then means no algorithm, only procedure is there, then the problem is said to be undecidable. If problem is said to be undecidable, if this means always halts means what? Halting to remission. Algorithm always halts, halting to remission also always halts. So if any problem, for any problem, if a algorithm or HTM exists, then the problem is decidable. Okay? If there is a procedure or a Turing machine, if there exists a procedure to solve that problem, or there exists a Turing machine to solve that problem, okay na? So you can say either procedure algorithm definitions or HTM Turing machine definitions. Okay? So a problem is said to be undecidable if there exists a procedure to solve that problem, or a problem is said to be undecidable if there exists a Turing machine to solve that problem. Okay na? So copy this, guys. Okay? Now, look at this, guys. These are the problems we are going to see. Okay? Now, all problems are decidable in the case of regular languages. This is decidable. Okay? All problems are decidable in the case of regular languages. Decidable. What are these problems? I will tell you. First, I'll fill this table, then we will go for the explanation. Okay now? So first we will see, okay, how to fill this table. Then I will explain clearly how to use this table. Okay now? So here membership problem, emptiness problem, finiteness problem, equivalence problem, regularity problem, completeness problem, ambiguity problem, disjointness problem. Regular languages, DCFL, CFL, CSL, REC, REL. You please copy this one. Already I told you, non-RE is undecidable languages. Non-RE, there is a no Turing machine exists. Sorry, Bhatnagar. So please, you can ask me the doubts after. Whenever I say something, some concept, you please focus on this. You can ask me the doubts later. Yes, you know RE. So you are saying that you have not included the definition. So non-RE is undecidable languages, undecidable, because Turing machine not exist. Okay? Copy the table. Copy it, guys. You want me to zoom? Okay, this is all problems are decidable under regular language. So I will explain what is this problem, how to use these problems. Okay. So tomorrow class is at 9 o'clock, 9 to, okay na? 9 to until complete, 9 o'clock. So others, whoever cannot be possible, please go for, anyway it is a theoretical theory only completely. So you can watch the recorded video, okay? Those who cannot attend, somebody has asked me, is going home, Sudeshna, I think. Okay, now guys, listen guys, DCFLs are also closed under everywhere, every problem except the last one, disjointness, except the disjointness. Okay, this is undecidable, okay? So DCFLs are closed under everywhere except disjointness, okay, except disjointness. What are these problems? I will explain, don't worry, that is my responsibility, and how to use these problems also I will tell you, okay? Now, CFLs are closed under membership, emptiness and finiteness. Membership, CFLs are closed under membership problem, means closed under means, sorry, not closed, okay, that is decidable. CFLs are decidable under membership problem, emptiness problem and finiteness problem, okay na? So CFLs are decidable, membership problem is decidable, under CFL. Emptiness problem is decidable under CFL. Finiteness, okay, also decidable. Whereas the all other problems are undecidable. All these remaining problems are undecidable. It is very easy to remember. Regular language are closed under regular language are decidable. Regular language are decidable under every problem. Regular languages are decidable under every problem. DCFL also closed. DCFL also decidable. I repeat, regular languages are decidable under every problem. DCFL also decidable under every problem except disjointness. Whereas CFLs are decidable. DCFLs are decidable. Membership problem, emptiness, finiteness, the remaining all are. And come to CSL and REC. CSL and REC only the membership problem is decidable. So membership problem of CSL decidable, membership problem of REC decidable, and except this, no, nothing is decidable. All are undecidable. This undecidable. And RE, membership problem, membership algorithm, RE undecidable languages don't have membership algorithm. RE languages don't have membership algorithm. So REL, nothing is decidable. REL, nothing is decidable, okay? Regular languages are decidable under every problem is decidable under regular language. DCFL also every problem is decidable except disjointness. CFL only 3, membership, emptiness, finiteness. remaining all are undecidable, and CSL and REC only one is decidable membership and all remaining are undecidable, whereas REL everything is undecidable, everything is undecidable. Okay. Copy. Done? Okay. We will see what are these problems. Copied? Now. Membership problem. Already we have seen it is the process of checking a given string W and a language it is a process of checking whether a given string W and a language L, are you following? It is a process of checking a given string W and a language L whether W belongs to L. Whether W belongs to L. This is called membership problem. Okay? This is called membership problem. Are you following? Whether W belongs to L or not. You can say otherwise W belongs to L or not. So, L or not. Or only here question mark, no problem. Okay. So, this is the meaning of membership problem. Okay na? Now, how to use this? Example. Let L is RE, let L is RE, a string, a given string W, or instead of this one E given, let L is RE and W is a string. Okay, W is a string. Is W belongs to L. Is W belongs to L. Okay, is W belongs to L. Are you following? See, what is membership problem? Process of checking whether a given string and a language, that string is belongs to L or not. Let L is RE and W is a string over sigma star, and even in E may not give this also, and is W belongs to sigma L. Okay, then listen, what is so L is RE and I will write in a different way. L is RE and a given string W and a given string W, L is a language, RE language, and W is W belongs to L, is W belongs to L. They can ask you like this also. Very simple, guys. Every year they will give you a question from undecidability. Okay, and Subi Goyal, you have asked me, I think, about that distribution of marks. I cannot say like this. Every year you will get one question from finite lambda and one question from guarantee push down lambda, one question from guarantee from undecidability and Turing machine. So minimum these question can, and remaining questions I cannot say. So finite lambda you can get 2-3 questions, regular expressions and grammar, finite lambda, PDA and Turing machine and undecidability, these questions. But minimum you will get 8 marks. Okay, maximum you may get, if you are okay, it may be 15 or maybe 17 only one time given. Usually they give minimum 8 to 9, 10, 11, 12 generally. Very rarely they give 15 to 17. Okay, now listen, how to apply this problem. How to apply this problem? L is RE and a given string W is W belongs to L. This comes under what? Membership problem. Is W belongs to L, membership problem. L is RE membership problem. RE membership problem is undecidable. Solved. How easy? You understand? If you can identify that this is comes under membership problem. Membership problem of RE is undecidable. So this is undecidable. You understand, guys? Okay, suppose I'll give you one more question. Okay, one more question. Example. This one. Okay, next. Let L is REC and a given string or I this time, and W belongs to sigma star. W belongs to sigma star. Is W belongs to L. So guys, this is what here L is REC. Okay, and W is sigma star is asking about W belongs to L. W belongs to L comes under membership problem of REC. Membership problem of REC is decidable. Only REL is undecidable. The rest all languages are decidable. So this is decidable. Okay, is decidable. Okay, copy this, guys. क्या? Hello. Copied. Okay, next we'll go for emptiness problem. Emptiness. emptiness problem. It is the process of checking. It is the process of checking whether a given language, okay, checking a given language L, a given language L, a given language L, emptiness, okay, is L equal to empty, is L equal to empty. This is the means whether the language is empty, that is the meaning. Emptiness problem, it is the process of checking a given language L is empty. Okay na? Example, we'll go for example. Let L is recursive, L is recursive, is L equal to 5, is L equal to 5, is L equal to 5. See, recursive, emptiness. So whenever the question is given like this, you must understand that L equal to 5, it comes under emptiness, it comes under emptiness. L is REC, emptiness, emptiness is undecidable. Are you following? REC, only CSL and REC decidable under membership. The remaining problems are undecidable. So REC, emptiness, REC is undecidable. So undecidable, okay, is undecidable. Okay now, suppose example, next example, let L is CFL, is L equal to empty. Okay, they ask you which of the following problems are decidable. So one L is REC is L equal to 5, and second L is REC and W belongs to sigma star is W belongs to L. So like this they can give you the questions. Okay, which of the following is oblique or decidable. So one option is this one, and second option is this one, like this. Okay now guys, so L is CFL, so CFL, emptiness, CFL, emptiness of CFL is decidable. Okay, right? Emptiness of CFL is decidable. So this is decidable. Okay na? Next, so emptiness problem is done. What is next one? Membership problem done, emptiness done. Next, finiteness. Finiteness. Finiteness problem. Okay, so this is a given language L, simple. I don't write it is the process of checking. Okay, a given language L, a given language L is L finite. Whether L is finite, otherwise you can say whether L is finite, whether L is finite means will it have finite number of strings, countable number of strings, that is the meaning. Okay, finiteness problem, finiteness. Okay, how to use this? Okay, example. Okay, example, let L is DCFL is L finite, yes, it is decidable, okay na, because DCFL, it is finiteness of DCFL, DCFL are not closed under, not decidable, only the disjointness problem only undecidable, the remaining all problems are decidable. So finiteness DCFL. Okay na? Next Next, let, next example. Next, L is RE. RE. Is L a finite language? This is what? Undecidable. Is undecidable because finiteness of REL is undecidable. Okay. Guys, are you following? Guys, following? So this is about finiteness, okay? Finiteness. So membership, emptiness, finiteness, equivalence. Guys, one more thing. These all problems also can be applicable on machines. Means you can apply on finite automata. Okay, and also here, and also grammar. Okay na? So finite automata and DCFL is what? DPDA na? DPDA. Okay, and DCFL, CFL is PDA, and CSL. What is CSL? LBA. I'll tell you. Don't, you need not write. You can write. This is STM. Okay, and this is what? This is Turing machine. Means you can apply all these problems on regular languages or finite automata or regular grammar. How, sir? Example. Okay, membership problem only. I'll tell you. Membership problem. Okay na? So take a note here. All these note. All the above problems can be applied on languages, comma, machines and grammars also. How, sir? How? Example. Okay, example. Let G be a context-free grammar. Is whether or is W belongs to L of G. Is W belongs to L of G. Okay, guys, listen. W belongs to L of G comes under what? Membership. Membership of a context-free grammar is what? Decidable. Only membership problem is undecidable in unrestricted grammar. Unrestricted. Okay, or otherwise, okay, we'll talk about some. This is what? Is decidable because context-free grammar is nothing but context-free language. Okay, it is decidable. Okay, now I'll give you in a different way. Okay, now guys, so we can apply on languages. Anyway, we are doing on grammars. This is example. And next, let M is a Turing machine. Is W belongs to L of M. Are you following? So M is a Turing machine, W is a string. I need not to say every time. Is belongs to L of M. What is the meaning of L of M? The language accepted by machine. Here L of M means okay, the language accepted by, because machine never gives strings. Machine machine accept the strings. Grammar never accept the strings. Grammar produce the strings. Okay, grammar produces and machine accepts. Language will have the strings. Language contain the strings. Grammar produce the strings. Machine accept the strings. Okay, L of M. The language accepted by the machine M or by Turing machine M. By the Turing machine M. That is the meaning of. Now guys, listen. M is a Turing machine. Is W belongs to L of M. Turing machine accepts REL. Membership of REL is undecidable. Is undecidable. Do you understand guys how to apply these problems? You can apply the problems on languages, on machines, on grammars. Okay? Next. Okay. Now copy. So are you copying simultaneously or shall I give you the guys? Did you copy this one membership problem? Guys, tomorrow 9 or 9:30, whatever convenient time, you just tell me. I'll start. And most probably by 2 o'clock I'll finish. Better I'll start 9 o'clock only. 9 to. Okay? Tomorrow class 9 o'clock. Okay then. Very good. This one? Or somebody has asked me slide please. Already copied na? Very good. So this one, take a note, this note. All the above problems can be applicable. Can be applicable. Very good. Okay. Now guys, this is about finiteness. Okay. We have done membership, emptiness, finiteness. Okay. Now equivalence. Okay. Equivalence problem. Equivalence. Okay. Given two languages, L1 and L2, whether L1 equal to L2. This is the meaning of the equivalence problem. Okay. Equivalence problem. Okay guys, given two language. Example. Let L1 and L2 are two regular languages. Two regular languages. Then, now, is L1 equal to L2? Is L1 equal to L2? Are you following? So, regular languages are closed under equivalence. Everywhere they are closed. So, it is decidable. It is decidable. Are you following? So, regular languages are closed and regular languages are decidable. Why I am saying, so just before this we have done na? So regular languages are decidable guys, decidable under every problem. Okay, now I change this. Now L1 L2 are two CFLs, context free languages. Then is L1 equal to L2? Now guys, the equivalence of context free languages, undecidable. Only context free languages are decidable under three problems. What? Membership, emptiness, finiteness. Membership, emptiness, finiteness. No other problem is decidable in CFL, whereas DCFL everywhere decidable and except disjointness. Okay, now you just remember in a very you just go however you remember, but you have to remember. So the best way is just regular languages are decidable under every problem. DCFL are undecidable only disjointness. CFL are decidable only first three problems. First three problems you remember. What are they? Membership, emptiness, finiteness. Because I told this in finite element also. You can remember in easy way. Membership, emptiness, finiteness, decidable. And CSL are only CSL and REC only membership, and RE nothing. Okay. Now, so this is, so what we have is an equivalence of CFL. Equivalence of CFL is undecidable. Okay, now guys, I'll go for one more example. Let M1 and M2 are two Turing machines. Then is L of M1 equal to L of M2. Guys, equivalence. M1, M2 are two Turing machines. So, Turing machines, REL are recursively enumerable languages. So, the language accepted Turing machine M1 and language accepted Turing machine M2 are equal or not. Equivalence of RE languages is undecidable. Okay, is undecidable. So guys, here I am not doing, I am expanding, that's it. Here problem is already done, everything is done. So when the table is given, I have done everything, but I am giving you more explanation way, because clear explanation I am giving you. So what is the problem? First of all, I am telling you, and how to apply. We can apply on languages, on machines, on grammars. So Turing machines, so nothing but REL, and REL is undecidable everywhere. So L of M equal L of M is undecidable. So similarly you can say grammar. Let G1 and G2 are two context sensitive grammars. Is L of G1 equal to L of G2. So context sensitive grammars are only decidable. Context sensitive language and recursive language are only decidable under membership, and no other problem is decidable. So again, grammars, nothing but context sensitive grammar, context sensitive language is undecidable. Are you following? Now, so this is about equivalence. Next, what did I give? Regularity or ambiguity or what? Yeah, regularity. Next, regularity. A given language L is L a regular? Is L a regular? That's it. This is the problem. Okay. This is the problem. How to apply? Example. Let L is REL, then is L a regular? Is L a regular? Okay. Let L is REL, is L a regular? L a regular. See, guys, REL, everywhere undecidable. Remember, guys, any question comes on decidability on Turing machines and REL and unrestricted grammar, blindly you say undecidable. Okay, na? So L is REL, is L a regular? Is undecidable. Is undecidable. Where it is decidable? Only two cases. Regularity. What are they? Regular. L is a regular. Is L regular? What is this question? I am in Delhi. Am I in Delhi? If I am asking the question like this, okay? L is regular. Is L regular? Yes, of course. Regular language is always regular. Suppose L is DCFL and is L regular? Yes, it may be regular, may not be regular. But in the case of DCFL, it is decidable. Okay, na? So next example. Let L is DCFL. Oh, here printing mistake, guys. Let L is let L is REL, is L a regular? Okay, na? Next, let L is DCFL, is L a regular language? Okay, so DCFLs are decidable everywhere. Decidable, regularity of a DCFL except disjointness, everywhere decidable. Okay, na? So guys, say okay, is decidable. Are you getting, guys? Okay, L is REL. A given language L, is L a regular language? Okay, next, guys, we'll go for next problem. What is the next problem? Okay, ambiguity. Ambiguity or completeness? What did he give? I'll go in order. Okay. Okay, guys, completeness. We'll go for completeness. Have you copied all? So what is this? A given language L is L equal to sigma star. Is L equal to sigma star means will L contains all strings of all combinations of input symbols. Is L equal to sigma star means Will it complete means will it contains all the strings over sigma star. That is the meaning of completeness. A given language L is L equal to sigma star. Okay na? Next, look at this example. Let L is regular. L is regular. Now is L equal to sigma star. So regular languages are decidable under all problems. Is decidable. Okay na? Next. This one example. Next step. Let L is REC. Okay. Let L is REC. Is L equal to sigma star? Is L equal to sigma star? Question mark. Okay. Now completeness only decidable under regular and DCFL. Then this is undecidable. Okay. This is undecidable. Is undecidable. Are you following, guys? Now copy this. A given language L is sigma star. Copy this. Regular problem. Copied? So all these problems we can apply on languages, machines and also grammars. So approximately 9 to 1, 1:30, maybe 2 o'clock, depends. So tomorrow will be the last class of TOC. Okay, done? Next. Completeness. Chalo, next. Next one, ambiguity. Ambiguity is decidable only under regular and DCFL. Ambiguity. ambiguity. A given grammar is ambiguous or not. So what is ambiguous? Already those who have attended for my compiler design class, you know, and those who have not attended, we will see in CD. Okay, now a given grammar is ambiguous or not. Okay, example. Let G's regular grammar is L of G ambiguous. Okay, yes, it is regular grammar is decidable. Okay, now next let G be a context free grammar. Is GB an ambiguous? Okay, this is undecidable. Is undecidable because context free grammar, ambiguity of context free grammar, ambiguity of context free grammar. If it is deterministic context free grammar, it is decidable. Okay, now so everything comes from the table. Okay, now take a note. A regular grammar can be ambiguous. Means it may be ambiguous or it may not be ambiguous. Okay, whereas a regular language can never be ambiguous. A regular language can never be ambiguous. Are you following? A regular grammar can be ambiguous. A grammar, example, what is ambiguity? If it has two or more parse trees. Okay, example, S there is A. Okay, go for S there is A S and S plus epsilon A. So this is regular grammar, but a regular grammar, it is right linear grammar. Okay, na? And it is S there is A and S there is A and epsilon. Here also A, here also A. What is the string here? A and here A. So it is A is ambiguous. Therefore, grammar is ambiguous. Okay, the grammar is ambiguous. And what is the language here? Language is A star. For this, can you construct a different grammar? Yes. This is the other grammar. This is unambiguous. Okay, na? This is unambiguous. Okay. So what is the statement here? For any regular language, guys, a grammar gives only one language. I repeat, a grammar gives only one language. But a language can have so many grammars. Example, A star. Here this is A star. And here also A star, na? Yes, I wrote here. This guy gives A star, this gives, but it is ambiguous. Whereas this also gives A star, but this is what? A S there is A S and epsilon only A, or S there is epsilon only epsilon, or A S plus A S then epsilon. Okay, so this whatever this grammar gives, all those strings are, whatever this grammar gives, all those strings will have only one parse tree. This grammar is unambiguous and it produces A star, and this grammar is also produce A star, but it gives S derives A, S derives AS in two different parse trees. So it is unambiguous. It is ambiguous. It is ambiguous and it is unambiguous. It is unambiguous. It is ambiguous because it is giving A in two different parse trees. It is okay. It can give two different parse trees for A. Whereas every string will have single parse tree. So this is unambiguous, this is ambiguous. Both are giving same language. Both are giving. So what I say, a regular language may have so many grammars, and on at least one of them, at least one of these is unambiguous. At least one of these is unambiguous. That is what I told you here. So a regular grammar can be ambiguous. Example, this is ambiguous. But a regular language can never be ambiguous. Means every regular language is unambiguous. Okay now? Now, so ambiguity done. Chale, copied. Ambiguity. Okay, ambiguity done. Then we'll go for last one. Any doubt, guys? Any doubt? Hello? Okay, now next one. So ambiguity done, then disjointness. 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 Given two languages, whether L1 intersection L2 equal to empty, means they don't have common, disjoint. Are they disjoint? Means no common is whether L1 intersection L2 equal to empty. This is called. So example. Okay. Let G1 and G2 be two context-free grammars. Is L of G1 intersection L of G2. So the disjointness of context-free grammars, the disjointness of context-free languages or context-free grammars, disjointness is undecidable. Only regular, except regular, everything is undecidable. So is okay. What is this? equal to is L of G1 equal to L of G1 intersect L of G2 equal to 5. What is this? Is undecidable. Is undecidable. Okay, na? Now, next, second example. Let M1 and M2 be two Turing machines. Is L of M1 intersection L of M2 equal to 5. Okay, so the disjointness of REL is and Turing machines and undecidable grammar all are undecidable. Okay, na? So that's all, guys. We have done this disjointness. And guys, hello. Here, all these problems. How many problems we have? 8 into 6, 48. These 48 problems we can apply on. Okay, actually 8 problems. 8 problems we can apply on grammar, language, machines. So 3 into 6, how many? Okay, 48. So 48 into 3. So 96 plus 48, whatever you count. Okay, my mind is not working. So I think 120, 144, na? 144, I think. 144 problems we have. Not only that, guys, not only that, the complement also we can do. Okay, na? Listen, if you remember this simple table, you can answer all these questions. These all problems we can apply on grammar, on language, on machines. Okay, so simply you remember regular languages are decidable, DCFL are decidable except disjoint, and CFL first 3 membership, emptiness, finiteness, and membership, emptiness, finiteness. Okay, next. CSL and REC only decidable under membership and RE nowhere. So guys, you can apply all these 8 problems on this regular language and finite means languages, machines and grammars, and also complement. What is complement? What is complement? Here, guys, listen. We have completed disjointness. Now, complement problems. All the above problems. Note. All the above problems can be applicable on complement also. What is the meaning of complement? Okay, example. Membership problem. I am talking about membership problem. Okay, now tell me guys. Let L is RE. Let L is RE. Whether and it is RE is W not belongs to L. That is complement, guys. What is membership problem? W belongs to L. What is complement? Is W not belongs to L. That's it. You know membership problem. What is membership problem? Yes, W belongs to L. Let it is a process of checking whether given language and string whether W belongs to L. Okay, belongs to L. What is complement? W not belongs to L. So L is RE and a given string W belongs to L. A membership problem of RE. So whether it belongs to L or not belongs to L, both are undecidable. You understand? So L is RE, is W not belongs to L, is undecidable. So some processor has told that W belongs to L, but W not belongs to L has not told. So is it decidable or undecidable? These doubts don't get in the examination. Okay, na? See guys, membership problem means W belongs to L. Its complement W not belongs to L. Also you can Say the same on the table. Okay, example one more. Let L is recursive is W not belongs to L. Yes, it is decidable. It is membership problem of REC. Okay, na? Simply one more. I'll go for disjointness problem. Okay. Example. Let L1 and L2 are two DCFLs, deterministic quantity free languages. Then is L of is L1 intersection L2 not equal to 5? L1 intersection L2. L of G1 means grammar should be given. Na? Language given means directly L1 intersection L2. What? The disjointness of DCFL is undecidable. Okay, na? Therefore, what do you say here? This is undecidable. If it is regular, let L1, L2 are two regular language. Then is L1 and L2 not equal to 5? So either L1 and L2 equal to 5 or not equal to 5. Both are same answer. Okay, na? So this is about. Okay. Guys, any doubt? So all the problems you can apply on complement. So guys, okay, so 8 problems on languages, machines and grammars. So 6 are there. So 6 plus 6, 18 into, okay, 8. You will get 144, na? 144. And again these 144. Okay, so many problems are there. 288. Okay, guys. Copy this. Okay guys, tomorrow we meet at 9 o'clock. Okay, so this and after this countability, uncountability, that one topic is there, then Rice's theorem. With that the topic will be completed. Okay, TOC will be completed. Rice's theorem, advanced Rice's theorem, and countability. These are the topics, and 90% I'll complete by lunch. Okay, 9 to 1:30. Okay, 4 hours. Okay, I'll complete tomorrow. So by lunch I'll complete 9 to 1:30, or maybe 2 or maybe 1. Okay, I'll show you, Subi. Just you copy this one first. Any doubt, guys? Do you understand this undisability topic? The previous topics concept. Do you all understand? Hello, guys. Undisability concept, whatever I have told you, the table. So halting problem, blank tape halting problem, state entry problem, post correspondence problem, modified post correspondence problem, MPCP. These all we will discuss. Okay, now this one, Subi, what is here? All the problems can be applicable on complement also. Okay, this is. Ambiguity we will do in comparison. So is it okay? Shall I go for the next slide? Copied. Slide before this, whatever, what this is, disjointness. Okay, so we all meet tomorrow at 9 o'clock. Thank you.